what is the expectation and variance of a hypergeometric distribution? Recall the expectation of a discrete random variable is nothing but summation over all values this x can take into probability x equal to x, or the probability with which it takes that particular value. So, now for a hypergeometric distribution, we are interested in knowing what is the expectation of this x. So, let us look at a case where x takes a value. So, I have summation over all x, and I know the probability of this x is m choose x, and I have a n minus m choose n minus x divided by n choose n. Now, we are just going to rewrite this following in a particular way. What are we going to do? I am going to write this as x, which comes from here. I am just going to write that. So, this is my x. I am going to retain that x here. I am going to write my m choose x as the following. I am going to write it as m into m minus 1 factorial by x into x minus 1 factorial. M choose x is m factorial by x factorial into m minus x factorial. I am just going to write that as m into m minus 1 factorial divided by x into x minus 1 factorial, and I am going to have it as m minus x minus 1. So, I will get only these two terms. So, now let us just focus on these two terms. I am going to get these two terms. I can simplify that into x into m divided by x into m minus 1 factorial divided by x minus 1 factorial into m minus 1 minus x minus 1. Okay. Now, let us look at the denominator here. Okay. Let us go to other color. The denominator here okay, let me go to the denominator here. I am going to write the denominator similarly as n factorial by n factorial into n minus n factorial. I am going to write this as n into n minus 1 factorial, and this I am going to write as n factorial into n minus 1 factorial and this n minus n factorial I am going to do the same thing. I am going to write it as n minus 1 minus n minus 1 factorial. So, we are just rewriting all these terms, okay, and this n minus m choose n minus x, I am going to rewrite it in this following way. I am going to rewrite it as n minus m factorial n minus x factorial to n minus m minus n minus x factorial. That is what this means. Okay. So, I am going to just write that as n. I am just going to retain it in the following way for now. We will come to it very soon. Now, if you look at the red portion, you can see in the red portion I can cancel out this term with this term, and here I have a m. So, only the red portion I can write it as an m into m minus 1 choose x minus 1. The red portion, this whatever is in the square here, I can write it as m minus 1 choose x minus 1. Now, let us look at the purple portion. For the purple portion, what I have is same. I have a n divided by n into, I can write this as n minus 1 choose n minus 1. Okay, because I have a n minus 1 factorial, n minus 1 minus n minus 1 factorial. So, this is what I have from my purple. Now, this portion, the green portion, okay, the green portion, I can again look at it as n minus 1 minus m minus 1, that is just my n minus m factorial, Okay. Similarly, I can write this as n minus 1 minus x minus 1. I can put that as a combination. So, you can see that the same thing I can write it as n minus 1 minus m minus 1. I can write n minus x as n minus 1 minus of x minus 1, I just get n minus x. So, in other words, this summation sign, I can write it as summation over all x of this kind. So, what can I do? I can see that this boils down to this m and n. I can write them separately. These are independent of x. So, that becomes m into n divided by n. I have a summation sign here, and that summation sign over x is going to be m minus 1, choose x minus 1, x greater than 0, n minus 1 minus m minus 1, choose n minus 1 minus x minus 1 divided by n minus 1, choose n minus 1. So, this is over all x minus 1 greater than 0. I know this whatever is inside is nothing but a probability mass function. So, whatever this term is in my green rectangle has to add up to 1, hence giving me my expectation of x to be n into m by n. I repeat, this is giving me the expectation of x is n into m by n. One way to view this expectation is I have a population of n of which m is of one type and n minus m is of the other type. From this population, I am choosing a subset of size n. I am choosing a subset of size n. So, here I have x is of one kind and n minus x is of the other kind. This is my subset n. So, you can see that initially in my overall set m by n was the proportion of items of type 1 in my population. I had m items of type 1. So, this is a proportion. So, this n is the sample size. So, n into m by n, this resembles this n into the number of samples or the size samples into m by n, which is telling me what is the proportion of items of type 1 in my population. This resembles, so if you recall, if x was a binomial with parameters n and p, I know that the expectation of my binomial distribution was x n into p. So, it is very similar to what we see here. In this case, I have if x is a Bernoulli distribution or if x is a hypergeometric distribution with parameter capital N, m and n, then the expectation of x is n into m by n or n m by n. So, now let us look at, we will not derive the variance of the hypergeometric distribution, but we are just going to look at a very simple way of looking at how to get hold of this variance. So, this variance is given by n into m by n into n minus m by n into n minus n divided by n minus 1. Let us understand this. Again, if I have a binomial distribution with parameter n and p, I know that the variance of x, where x is a binomial distribution, is n into p into 1 minus p. If I have a hypergeometric distribution with n, m and n, I know that the expectation of x is n into m by n, where this m by n is in a sense the proportion term, which I can relate this proportion term to this p here, where p also represented a probability or proportion. So, if I am going to look at a similar term for the variance of x, I know it is going to be n, p is m by n, 1 minus m by n, 1 minus p. So, if I am looking at n p into 1 minus p, it would be n p into 1 minus n by m, which is n, into m by n into n minus m by n. You can see that this is precisely what I have here. I have n here, I have m by n here, I have n minus m by n minus n. We have an extra term here, which is n minus small n by n minus 1. Now, let us look at this n minus n by n minus 1 more carefully. I can write this as 1 into 1 minus n by n divided by n into 1 minus 1 by n. I have just removed the n outside. So, these two cancel out, this n cancels out with this. So, I have a 1 minus n by n divided by 1 minus n. Now, if n is very, very large, or as n tends to infinity, I know that this term goes to 0 and this would just remain as 1 minus n by n. Now, second thing, if n is very, very small as compared to n, again this would go to 0 and I just have a 1 here, which tells that this entire term, if n is very small as compared to capital N and n is very large, this entire term tends to 1. I repeat, if the sample size is very small as compared to my population size, then this term, it actually tends to 1 and you can see that this variance of x in that case would just be n into m by n into n minus m by n, which resembles my binomial variance. Now, what does it mean that if n is equal to 1? Now, if n is equal to 1, then n minus n is just going to be n minus 1 by n minus 1. In another terms, n equal to 1 would mean that I am just sampling only, I am doing only one element, I have sampled only one element and that would just resemble a Bernoulli trial. I just have one, n takes only one value, it is just a single Bernoulli trial. I do not have the notion of independent trials at all here. Now, the next, so the first extreme case was n equal to 1. This is again just one Bernoulli trial and you can see in that case, it just my variance of x would be just m by n into 1 minus m by n, which is the same as the variance of my Bernoulli trial, which was p into 1 minus p. If you recall, if y is a Bernoulli trial with parameter p, then variance of p, the Bernoulli trial is p into 1 minus p. Now, the next extreme case which we can discuss here is what would happen if n equal to n. N equal to n says that you are sampling the entire population. Small n equal to capital N says you are sampling the entire population. When I am sampling the entire population, what would happen? I do not have different samples. Different samples only is going to give me the variance of x. X is just going to take a single value. So, the variance of x in that case is going to be 0. If n equal to n, you can see that if n equal to n, I have n minus n which is equal to 0, which results in variance of x be equal to 0. So, you can see that this variance and the expectation of my hypergeometric variable bears a very close resemblance to the expectation and variance of the binomial random variable. So, let us look at the graph of the probability mass functions of the hypergeometric random variable. So, we start with the case where I have x is a hypergeometric random variable. I am going to represent it as just a hyper with n equal to 20, m equal to 4 and n equal to 5. So, from this box of 20, I have only 5 which are of one kind. I have the others which are of the other kind. So, I have 15 which are of the other kind. I have only 4, sorry, I have only 4 and 16. I have 4 which are of one kind and I have 16 which are of the other kind. Now, from here I am sampling a sample of 5 points. So, if what is the chance that all the 5 would be purple? That is going to be 0. So, my x cannot take the value 5. What is the chance that all the 5 is going to be 0? You can see that all the 5 are going to be orange. It has a chance which is about 0.23. The chance that only one is purple and everything else is going to be orange is much higher. And you can see that the chance that everything else, that I take 3 or 2 of purple, 3 of purple and all 4 purple have a much lesser chance. Intuitively, you can see that if I am going to sample from this box, the chance I get an orange ball is much higher than the chance I get a purple ball, because I have more orange balls to purple balls. Hence, you can see that the chance I get an orange balls will say that the chance x takes a higher value is going to be lesser. X is the number of purple balls. So, x taking this number of purple balls is going to be the number of purple balls taking 4 is going to be lesser than, it's going to be much lesser, and you can see that this is how my probabilities are. So, you can see that x takes the value 1, which is 1 purple. It is very likely that this can happen, but higher values it is not happening. Suppose I flip this situation. In the same thing, I have now my m equal to 16. So, go back to our initial example and I had now m equal to 16. So, from a box of orange balls, the chance that I pick 4 orange balls is much higher than picking no orange ball. So, you can see that my entire probability mass function has actually reversed, or you can see it is almost a mirror image of what we had here, n equal to 20, m equal to 4 and n equal to 5. It has a mirror image when n equal to 20, m equal to 16 and n equal to 5. Now, let us look at the case where n equal to 20 and m equal to 10. Now, in this case, I have m by n, which is 10 by 20, which is equal to 0.5. So, here you see that my box has equal number of both types. When I have an equal number of both types, I get a symmetric distribution, and I am sampling 5 balls. So, you can see that I get a symmetric distribution where the probability of me having 2 or 3 is the same, and you can see that this is a symmetric distribution because I have both of the same type. So, these are the shapes of the distribution function. Similarly, for the same m equal to 20 and n equal to 10, so my m by n is again 0.5. You can see that here I have a symmetric distribution again, but with more bars because my sample size has increased now from the earlier case. Again, for the same m and n, you can see that for a different, again my m by n is half here and my sample size is 10. So, again you can see that the distribution is again symmetric, which was very similar to what we had here. The values n takes is again between 0 and 10. Again here also the values n take would be between 0, x takes is between 0 and 10. And you can see that the probabilities of is also very similar. So, both of them have a similar distribution. no matter what is your n and m, as long as m by n is half, I have a similar probability distribution. Now, what would happen in this case? Again, my m by n is going to be 1 by 2, and you can see that the probabilities change, but this distribution pattern remains the same. So, what I want, the key takeaway is, as long as my m by n is half, I have a symmetric distribution around this point. You can see that that is true for most of my values. Again, n takes a value between 0 and 10, and I have, you can see that n into m by n in this case is 10 into half, which is 5. So, the center is around 5. In this earlier case, again here it was 10 into half, again the mean is at 5. In the earlier case, again the mean is at 5, which is again n into half, which is 10 into half, which is equal to 5. So, in all these cases, you can see that the mean was at 5 and the distribution was symmetric around 5. N was a constant, 10. I kept varying capital M and capital N such that m by n was always half. We saw that we had a symmetric distribution centered around n into m by n, which is just 5. So, in summary, what we have seen is, if x is a hypergeometric distribution with parameter capital N, which is a population size, small n, which is the number of units of one type, and small n, which is the sample size, then the expectation of x is n into m by n, and the variance is n into m by n, 1 minus m by n into n minus n by n minus 1. Now, let us look at a binomial distribution. This is something which we have already seen. If y is a binomial with parameters n and I am putting p equal to m by n, then I know my expectation is n into m by n and variance is n into p into 1 minus p, which is n into m by n minus m by n. So, if I look at variance of x divided by variance of y, I see that the expectation of x and expectation of y are the same. If I divide the variance of x with variance of y, I just get a n minus n by n minus 1. All other terms cancel out. So, for n equal to 1, I see that it is just a Bernoulli trial, and for n equal to n, I see that by variance of y, x is, this is equal to 0. And we also saw that if n is very, very large as compared to n, then I can, this term vanishes and I can see that a hypergeometric NMN is about the same as a binomial NM by n. Now, let us understand the difference between the binomial and hypergeometric, because we see that the hypergeometric, the expectation and the variance of the hypergeometric resemble that of a binomial. So, it would make sense for us to look at how or when as a binomial distribution and a hypergeometric distribution different from each other. So, now let us start by looking at the probability mass functions. So, here I have n equal to 5, the blue represents the binomial distribution. So, y is a binomial with parameter n equal to 5 and p equal to 0.5. I know p equal to 0.5 would give me a symmetric distribution. The blue bars represent the probability mass function of the binomial distribution, and the red bars represent the probability mass function of my hypergeometric distribution. Again, I know my x in both the cases would take value 0, 1, 2, 3, 4 and 5. If you look at the range of n by n, it is about 1%, n equal to 5 and this is 500. So, you can see that n is very small as compared to your capital N. We can see that the distribution of the hypergeometric and the binomial distribution are almost the same. This is what we have just established when it is about 1%, that is 0.01. So, you have this term n minus n by n minus 1, which was nothing but 1 by n minus n by 1 minus 1 by n. This is what I had. So, this n by n minus 1 by this term is 1%. 1% would just mean that this is about 0.01. So, I have this tending to what my variance is the same as that of the binomial distribution. Now, let us look at a term when n equal to 25 and p equal to 0.5. Again, I get a symmetric distribution. N takes the values, again x, if y is my binomial distribution, y takes the values 0, 1, 2 up to 25, and this probability mass function is again given by my blue bars here. Now, x is a hypergeometric with parameter 500, 250 and 25. Again, my x also takes value 0, 1, 2 up to 25. Remember, it is minimum of n and m. It is 25 and 250, it is 25. So, both x and y take the same value, n by n is 5%. Here you can see a slight difference, the blue bar and the red bar, you can see a slight difference which is there between the blue bars and the x bar. The expected value although remains the same, or the center of the distribution remains the same. Moving forward, when we look at this, again when I am looking at the same n equal to 50, again y is a binomial with parameter 50 and 0.5. My mean is at n into 5 by 10, which is about 25. The mean is at around 25. Again, my n into m by n is again going to be 50 into 20, 250 by 50. It's the same. The mean for both my hypergeometric and my binomial distributions are the same, which is at n, which is equal to 50, m by n, which is going to be my 25 by 2, which is nothing but 0.5. Okay, both the cases it's the same. So, the mean is at the same, and you can see here again even though the shape of the distribution is the same, the probabilities are different. You can see that the red bar is slightly higher than the blue bar at the middle, and as it goes away from the middle, the blue bar is higher than the red bar. It is not exactly the same as the hypergeometric. You can see that the red bar. Now, let us look at this term n minus n by n minus 1 here. So, this was again 1 by 10%, which is 0.1 by 1 by 1 by 500. So, you can see that the variance is actually a percentage of the variability of my Bernoulli distribution. Now, I again increase this, my n equal to 250 here. I am just drawing the range from 100 to 150, but actually my y, which is a binomial with parameter 250 and half, is going to be, would take the value 0, 1, 2 up to 250. X is a hypergeometric with parameters 500, 250 and 250. So, again my x will also take the value 0, 1, 2 to 250. The mean for both x and y is n, which is equal to 250 into m by n, which is 250 by 500, which is equal to, the mean is just 125. And you can see that the mean for both these distributions is at this point, both the binomial and the hypergeometric. But what you can notice here is the binomial distribution is having more variability in terms of the bar. So, if I were to connect this using a blue bar, of course, I would find a curve of this kind. I am just connecting the points to just show what would be the difference. Actually, these are only bars, and connecting them by things does not, it is not a continuous curve, it is just bars, but just to give you an idea, I am connecting them. And you can see that when we connect these things, you can see that the red one has a higher probability in the middle. The means are the same, both of them are symmetric, but the binomial distribution has a higher variability than the hypergeometric distribution. I have just restricted it to 100 to 150. I would have smaller bars for both the distribution on either side. Okay, that is something, it is almost 0 at a particular, after a particular side range. Now, again in this case, if you look at what is your n by n, n minus n by n minus 1. So, this is nothing but 1 by n by n by 1 by 1 by n. This is n by n is about 50% divided by 1 minus 1 by 500. You can see that this value is what we are multiplying. So, the variance of x is equal to 1 by 1 minus 0.5 by 1 minus 500 times variance of y. So, that is why the variance is actually it's coming down. The expectation of both the binomial and the hypergeometric remain the same. So, in summary, what is important when we move from a binomial distribution to a hypergeometric distribution is to first understand we are sampling without replacement. When we are sampling without replacement, we lose independent trials, we lose identical distribution. The expectation is n into m by n, the variance is n into m by n into 1 minus n minus m by n into my n minus n by n minus 1. For n very small than n, the hypergeometric with capital N, N and M is almost or just about a binomial with parameter n and m by n. This is what we have seen. So, the next thing which you are going to understand is 3 more important distributions. The first is the Poisson distribution, the next is the negative binomial distribution, and the third is a geometric distribution. These are the 3 distributions which we will discuss in detail.